All right, so in this lesson, we're going to look specifically at series circuits. So what makes up a series circuit? And then I want you to be able to calculate voltage, current, and resistance at each point in the series circuit. Before you watch this video, I would advise you to watch the explanation that matches series and parallel circuits to water circuits. I find that a very, very helpful video to explain what's happening, and I think it actually will give you a better understanding before you jump into the math. So this video is more focused on the math that's required in order for you to do the calculations for a series circuit. So first of all, what is a series circuit? So in this circuit, you can see that we have a battery here, and we have 3 light bulbs all connected by a single, in a single line. Okay, so we could say 3 light bulbs on a single wire. This is a series circuit. There's only one path for the current to flow between each item. Okay, so there's only one path from the battery and back to the battery. There's not multiple ways for the electric current to flow. So the current must flow through each of the batteries, and we'll notice here it's marked with conventional current, which is from positive to negative, which is, I really don't like that because it's not the correct way, but it is how we define current. So there's one path for current to flow. So Kirchhoff was a scientist who studied electricity, and he came up with 3 laws that relate series circuits, and they relate to current, voltage, and resistance. So first of all, if we think of it like water, there is one path for the current to flow, or for the water to flow. So the current, what goes in must come out. The flow must be the same everywhere. Okay? The flow can only flow as fast as is the sum of the resistances. So we'll see here that the current, IT, is current at the battery. So we could put that in here. So IT is at the battery. Total current, or battery current, is the same as the current at position 1, position 2, and position 3. So we'll call this one 1, 2, and 3. So we'd have I1 here, I2, and I3. Okay, so all of the currents are the same in a series circuit. None of the bulbs have different currents. I have a really good little kit that kind of shows some of this stuff, and I'll see if I'm able to share some of it online. I don't know if I can, but you're more than welcome to pop by the office, and I'm happy to loan out my snap circuit for you to plug in and kind of play with a few of the pieces. There's some great resources that are available with those kits, and usually I would have students spend a day working with them. So I may find a way to do that, but I only have 8 kits, so it's a little complicated with all the COVID distancing required. So that covers current. Current's the same everywhere. Now voltage, the total voltage, or the voltage at the source, is equal to the voltage that drops across position 1 plus the voltage drop across position 2 plus the voltage drop across position 3. So voltages add up. So if you want to know the voltage at the source, you can add each of the individual voltages, and that will give you your total voltage, right? So the push comes from the battery, and each bulb decreases that push until there's no push left. Now, Req is the equivalent resistance, and it determines how much current is drawn from the source. So as soon as those wires are connected, current wants to flow from one end of that battery to the other. So the amount of current that's allowed to flow depends on the sum of the resistances that are in the path. So that's what we have here. We have resistor 1 plus resistor 2 plus resistor 3. So for a series circuit, current is constant, voltage adds, and resistance adds. So those are the 3, the easy pieces. Those are questions that you could be asked to know for a block exam, and they are not provided to you. Those are expected to be memorized. And usually I would always ask students to memorize them when we did in-person testing. So these would be really, really, really good, these 3 laws, to throw in a memorize list. Okay, now some of them you don't have to memorize too much. So if you think, well, current is the same everywhere because there's only one path. If you know the definition of a series circuit being only one path for current to flow, that should help you remember that current is the same everywhere, and then resistance adds and voltage adds. Parallel circuits are going to be a little different. We'll deal with them in a separate video just for the sake of simplicity. All right, so I've got 3 questions, example questions for us to calculate. They're nice and simple questions. They shouldn't take us too long to do. And then we'll do some combination circuits next week. So we'll put everything all together and add a little bit of complexity. All right, so given the circuit below, I want you to calculate the equivalent resistance, the current drawn from the battery, and the voltage across each resistor. So when I calculate these ones, and you'll notice in the worksheet that I've posted, I've got a chart. Okay, and it's got 3 columns in it. I guess I should say 4 columns. So the first column, we have a column for E, or for voltage. We have a column for current, and I have a column for resistance. And we're going to put each of these in their base units. So E will be in volts, current is going to be in amps, and resistance will be in ohms. Then we're going to label each resistor. We have resistor 1, resistor 2, resistor 3, 4, and our total. Extend our lines. I find this is really helpful for keeping information organized. And even for testing purposes, I'll often use it just because it helps keep everything categorized for us. Now we have 5 resistors, and we can fill in their values because we know their values. So 1 is 20, 2 is 20, 3 is, oops. This is what happens when my mouth and my hands don't work together. 3 is 20 as well. 3 and 4 are both. And then 5 is 10. So we can already apply one law. And then the total, actually, instead of RT, I don't really want RT. I'm going to do, this is the source. Okay, or the total, if you want to think of it that way, okay? So we know from our equation that all the resistances in a series circuit add up. So 20 plus 20 plus 20 plus 20 plus 10 gives me 90 volts. Sorry, 90 volts, 90 ohms. I really am getting myself all muddled up with words tonight. I've been doing recordings all day long, and sometimes things just get a little muddled. Now, we've put in all the information that we have here. We have this piece of information here that at the battery we have 9 volts. So that would be our source or our total. Now we need to figure out, well, so we've got the equivalent resistance. We've calculated that. That's 90 ohms. What's the current drawn from the battery? Well, the current drawn from the battery goes right here. You'll notice at the battery, I know voltage and I know resistance. So I know at this point, my resistance is 90. So using Ohm's law, we can apply Ohm's law at any point in this circuit. So Ohm's law says that E equals IR. And this is an example of using other resources, and some resources use V and some resources use E. I apologize for the lack of inconsistency. So E equals IR. So we have 9 is equal to I times 90. Divide both by 90. And current is equal to 9 over 90, which is 0.1. So you have 0.1 amps. Now that we know the current in one place, if you remember back to Kirchhoff's laws says that current is the same everywhere. So we have 0.1 everywheres in this particular circuit. Because there's only one path for the current to flow, so the current can't change throughout the circuit. Now that we know current and resistance, we can calculate V. or E. E equals current times resistance. So just multiply the two together. So at resistor 1, the voltage is 0.1 times 20, which leaves us with 2 volts. 0.1 times 20, we have another 2 volts. 2 volts, 2 volts. 0.1 times 10 leaves me with 1 volt. According to Kirchhoff's laws, if we add the voltage drops together, we get the voltage of the battery. Is that true? Well, 2 plus 2 plus 2 plus 2 is 8, plus 1 is 9. So yes, it is true. So that completes our table. So there's just a couple of things you can use to check. I like using, double checking a couple methods. But I really like it to be able to put my information in, and then for each line or each resistor using Ohm's law. Let's look at a second example. This time we only have 3 resistors. So I'm going to set up the same kind of chart. So we have our total, resistor 1, resistor 2, resistor 3, and we have voltage, current, and resistance. All right. So we know, again, we have a 9 volts at the battery, so that's at our total. And then we have 100 ohms, 300 ohms, and 50 ohms. Now the total resistance seen in this circuit is going to be 450 ohms. We just add them together, okay? We're just adding the column down. So resistor 1 plus resistor 2 plus resistor 3. Now we can find out what the current is from the battery. So current is equal to voltage divided by resistance, which is equal to 9 volts divided by 450, which gives us a current of 0.02 amps or 20 milliamps. And the current is the same everywhere because we have one path. Now we can calculate the voltage drop across each resistor. So we know the greater the resistor, the higher the voltage, the greater the voltage drop, or the more it will reduce that push. So we should see that's true. So 0.02 times 100 is going to leave us with 2. 0.02 times 300 leaves us with 6. 0.2 times 50 leaves us with 1 volt. 2 plus 6 plus 1 leaves us with 9. So we have a double check there. That is the correct value. So I'm using, for each line across, I'm using Ohm's law. As I add things down the column to get my total, I have to think of Kirchhoff's laws. So Kirchhoff's law says current is the same, resistance adds, and voltage adds. And then we use Ohm's law to go horizontally. Hopefully that makes sense to you. A nice easy number, so we don't have a lot of complex calculation. And then another quick one. Well, this was a little, this one I really like, and I like the way it's laid out. This is the other way I'll lay things out if I don't use a table. This is one of my favorites. And in this question, we have a whole bunch of random pieces that are missing. So you'll notice they didn't give us all the resistors. They didn't give us all the voltages. They didn't give us currents, but we can calculate the missing values. So this one is a little trickier. So the first thing I'm going to do is find a spot to use Ohm's law. I struggle to talk and write, so sorry for the pause. So did you find the spot to use Ohm's law? This is the spot to start, okay? Because we know voltage and we know resistance, we can calculate current. So current is equal to voltage divided by resistance, or V over R, which is equal to 6 over 3, which is 2 amps. Now that I know that, what did Kirchhoff's law say about the whole circuit? So 2, I want you to ask, what's the same? Everywhere. In this case, it's current. Okay, so current's the same everywhere. So the current at 1 equals the current at 2. So I can plug in 2 amps there. It's equal to the current at 3. That's equal to the current at the source. So current is the same everywhere, so we can put that in. In this case, we have current. And then 3, use Ohm's law for the missing pieces. So use Ohm's law where you can. So here, we know voltage and we know current, so we can calculate resistance. Resistance is equal to voltage divided by current, which is equal to 12 over 2, which is equal to 6 ohms. Okay, so we have 6 ohms there. Over here, we want to know what is the voltage drop. So volts is equal to E times I, which is 2 times 2, which is 4. So we have 4 volts at this point. And now we have one last piece left. So we know all the voltages have to add up to the source. So we know all the voltages have to add up to 12. So we can say, well, 12 is equal to 6 plus 2 plus voltage 3. Whoops, let's do 6 plus 4 plus the voltage at 3. Well, let's just subtract them. 12 equals 8 plus voltage at 3 minus 8. 4 is equal to the voltage at 3. So this is 4 volts. Now that we know that's 4 volts, we can go back and we can use Ohm's law again. So resistance is equal to voltage over current. See if we can get back here. No, let's see. Not sure what's going on here. Let's try her again. There we go. We'll finish off, sorry about that. We'll finish off our last piece of information. So resistance, so we were down here, we were figuring out what's resistor 3. Resistance is voltage divided by current, which is equal to 4 over 2, which is 2. So 2 ohms. And there's all of our pieces calculated. So you're just kind of breaking it down and then using Ohm's law, thinking, where can I use Kirchhoff's law? These ones are a little bit more complex. So I don't really have any for you to do practice of these ones, but we will see this type of question come up in your lessons next week. So I'll give you several of these ones, but they're really, really good problem solving strategy thinking. Where should I start? So start the simplest spot and then work your way up to more complex pieces. Very much the same way you do troubleshooting in a vehicle. Start with the most simple scenario and then work your way up to the more complicated pieces. So that finishes off this section. If you have any questions, please don't hesitate to let me know. And we'll move on and we'll do a quick section with some parallel circuits. The math for parallel circuits is fairly straightforward, but does have a couple of pieces that calculating resistance is slightly more complex. I'm going to give you a tip with your calculator in order to do that.